whole series of bridges. All these bridges serve the same purpose, and yet they're all different. That's because each one had a different designer. A bridge is one of many structures that first take shape on a designer's drawing board. Among them are some very familiar buildings. Your school, for example. It may not look quite like this one, but it serves the same purpose. Then there are the structures in which we live, our homes. Again, yours might be very different to these, but they're all designed to do the same job. And then there are the offices where people work, all different, but all providing the same function. But not all the structures you see come off a designer's drawing board. Nature has provided many more. Natural structures, too, are all different. In fact, they're all designed to suit a particular way of life. But what is a structure, and what is it for? We can get some clues from nature. These flowers are held up by stems, and so they're easily seen by the insects which visit them and help fertilization. A long neck holds up a giraffe's head, enabling it to get the food that other animals can't reach. Our eyes are held high above the ground, giving us a better view of the world. It seems that holding up is important in nature. It's one of the main jobs of a natural structure. It's also a job of man-made structures. A water tower holds up a tank of water to supply the surrounding houses. And a pylon is specially designed to hold up the cables that carry electricity across the countryside. But holding up isn't the only job of a structure. Here, the most important job is to span. Nowadays, it's possible to span enormous lengths with the absolute minimum of material. But what about span in the natural world? If you could see through a horse, you could see its skeleton. The backbone spans between the front and rear limbs. These fern leaves span to catch the light. The long bones in our arms span so we can reach out. But a structure often does more than just supporting and spanning. The other job a structure is designed to do is to enclose. In a cathedral, the walls and roof enclose an enormous space. On the airfield, a hangar has to enclose an enormous space to house the aeroplanes at garages. The leaves of this pitcher plant enclose a space full of water, which acts as an insect trap. Snails have a shell to enclose and protect the soft parts of their body. A skull encloses and protects the delicate tissues of the brain. So structures do certain specific jobs. They hold up, they span, and they enclose. And it's not only in a natural world, man-made structures do the same jobs. They also hold up, span, and enclose. In designing a structure, an architect or engineer must take into account not only the jobs it has to do, but also the forces it will have to resist. The force can be due to the weight of the structure itself. And it can be very large. In the man-made world, it can add up to thousands of tons. As well as their own weight, some structures carry loads. These additional loads impose extra forces on the structure. Although this mother doesn't seem to think her load is an imposition. In the man-made world, the imposed forces can be very large. This structure is built of brick. We can easily find out how bricks behave under an increasing load. They can resist a large force pushing down on them before they break. Sometimes the forces can be short and sharp. We call this kind of force an impact. So structures have to stand up to three types of forces. Forces due to the weight of the structure itself, forces due to loads imposed on the structure, forces caused by impact. And of course, the same forces act on man-made structures. When designing a structure, the architect or engineer has to choose materials that will withstand all kinds of forces. So we need to know how materials behave when forces act on them. We need to know their properties. How do you think these four materials will behave under a force? Metal, biscuit, a plastics material, and jelly. First, the metal, steel. It resists a pulling force. It's strong. Biscuit, on the other hand, is weak. Obviously, strong and weak are opposite properties. But what about a plastics material? It's certainly got strength, yet it bends. It's flexible. Flexibility is another property used to describe building materials. A plastics material is strong, yet flexible. Biscuit doesn't bend, it's rigid. Rigid, yet weak. And jelly, it's flexible and weak. Among the best building materials are metals like iron and steel. Unfortunately, these metals have only been available cheaply and in large quantities for the last 200 years. Before that, builders had to rely on natural materials. For instance, wood. It's got strength and it's not too flexible, so it can span reasonable distances. But although it's been used as a building material for a very long time, wood can rot and decay. The best natural material is stone. Stone, too, is strong and rigid. This structure has survived for thousands of years. In fact, some of the most impressive examples of stone buildings are the great Gothic cathedrals built hundreds of years ago. They support, span or enclose on the largest possible scale in stone. But when steel became available cheaply, everything changed. Revolutionary new designs were possible. Not only greater spans, but greater heights and larger enclosures. This is because steel can resist certain forces on a large scale. In this experiment, a specially prepared steel test piece is being pulled by the large jaws. The steel stretches, but it's not until the pull reaches about 150 kilonewtons that the sample breaks. Now, this tremendous strength enabled designers to build a completely new type of bridge, a suspension bridge. The roadway hangs below the main supports. The Clifton Suspension Bridge, which spans the Avon Gorge in Bristol. The roadway pulls down on steel suspension chains. They're made up of links held together by bolts. But when this was built, the strength of the steel they used limited the spans to about 200 meters. Nowadays, very strong steel wire is available, which can resist much greater pulls. The great strength of modern steel wire makes possible spans of 1,000 meters and more. But for most normal structures, huge spans are not required. But it's not just the strength of the material that makes a structure strong, its shape is important too. Hump bridges span by an arch. Arches built of bricks can span over 40 meters. Stone or brick arches were first widely used by the Romans. But what makes a brick arch stand up? And not only stand up, but also support large loads. Could it be anything to do with the way the bridge is built? Let's look at a bridge built differently. It collapsed because the bricks can tilt. So the success of the arched bridge comes from the way the bricks are arranged. By the way, we haven't cheated. The bricks aren't glued together. This piece of card can't even support its own weight, never mind an added weight. But fix it into an arch shape, and it can even carry an extra load. The strength of the arch shape is used in this new material. The corrugated layers act as a series of arches. The resulting material is very light because it's made of cardboard, yet very strong because of the arch shapes. Very, very strong. But this shape isn't new. It's existed in the natural world for millions of years. This is the magnified view of the cross-section of a plant stem. The structure makes the stem light, yet strong. But there are now structures which do have new shapes. Not only does concrete take up the shape of any mould it's poured into, it can also be strengthened by iron rods running through the mould. So reinforced concrete is a new material for new structures, which is shaping a new world.